Here I'll show you how to create a latent variable growth curve model using Stata. And we're going to focus on the linear model here. There'll be another section that describes how to do quadratic growth, but in here we're just going to stick with the basic linear growth curve. Now, in the more recent versions of Stata, they have an SEM component to it. In previous versions, that hasn't existed, so you'll need an up-to-date version of Stata in order to do this. Stata version 13 has it. So we're going to start here, go to Statistics, and go to Structural Equation Modeling, Model Building, and Estimation. And this is going to pull up our Model Builder window. And we're going to start with this here, an Add Measurement component. This is going to be our quickest way to create, start creating our growth curve model. So I click on that, and then I click somewhere on the Builder window, and I'm going to name this latent variable, and I'm just going to name it int for intercept. And now we're going to select all the measurement variables. Select variables. You could specify the number of variables, and that wouldn't populate the boxes with the variables, but we're going to select the variables so that we have that. So I'm going to go down, and what we're going to be looking at is wife's marital quality over time. We have 7 waves of marital quality data. So I'm going to click each one of these in order, and it's going to populate my box up there with them. And here we're going to make sure that this box is checked. Do not estimate constants. Now often you'll see this box as default is unchecked. I've been doing some growth curve models today, so it's remembered that, and it's checked that box, kept that box checked. But we don't want to estimate the constants. For growth curve modeling, for the indicators, we constrain those to be 0. So that's exactly as it should be. So I click OK here. And oh, I can't name it int. I forgot that. Int is reserved for something else, so I'm going to call it intercept. And that should be fine. Okay, so now we have our intercept there. I'm going to move this over so we can see everything there. And then I'm going to just select this one and scoot it down here because we're going to put our slope over here. But first, let's go ahead and select all of these. And as you'll remember, these all need to be 1. The intercept is the constant effect at each time point and represents the average when the slope is 0, and we'll look at that in a minute. So I've just selected all those, they're all blue, and up here you can see that I can add in a constraint. This little lock means constraint on this weight. They have a beta there for that. So I'm going to type in 1 and hit enter. It's important to hit enter in Stata. If I just went off without hitting enter, that wouldn't be safe. But I hit enter here, and you can see that all of these are now 1s. Now let's add in our slope. So we need to add an extra latent variable. I'm going to put it right there. And then, why don't I double click on it? And I need to estimate its mean. Remember, for growth curve modeling, the means of the slope and the intercept are essential. Often it will not estimate the mean. Latent variables will not estimate the mean. They'll just estimate the variance. But for this, for growth curves, we really do want to estimate the mean of these. And I'm going to name it SLOPE, slope. Okay. Now I'm going to do the same to the intercept in terms of estimating the mean. Make sure that's checked. All right, next what I'm going to do is I'm just going to add the paths from slope over to the different indicators of marital equality over time. And then what I'm going to do is, of course, I'm going to select these, and I need to give them weights. And because this is linear slope, we are going to fix this at 0, and the next one at, I actually can just go up here to that 1. The next one is going to be at 2, and then at 3, 4, 5, and 6. So we have these at 0, 1, 2, 3, 4, 5, 6. And we also want to correlate the intercept and the slope. The idea being here that where you start out probably influences how much you're going to change over time. You could think of this in terms of ceiling or floor effects, or maybe you have some other hypothesis about why your initial level, your intercept, should influence your rate of change. Now again, remember the intercept is the average when x is 0 or when the slope is 0. And because the slope here, we've constrained this one to 0, the intercept, the mean of the intercept, is going to represent the average marital quality at the first time point. And that's very convenient. You could actually make any of these 0. So let's say you made this one 0, then this would be -1, -2, and -3. This one would be +1, +2, and +3. It would still be linear, but you would have this midpoint right here. And sometimes people would like that because there's something happened at this particular point that they want to make that their 0 point. They want that the mean of the intercept to represent that. It won't change the model fit at all by doing that. It's just what you want the interpretation of your intercept to be. So let's go ahead and fit this model. We're going to do maximum likelihood with missing values. So if somebody has at least one piece of data, they had one time point here, they'll be included automatically. So we're fitting our saturated model first, and that's the model with everything related to everything else in the model. Baseline model, which is none of the variables are related to any of the other ones. And then the target model, that's the model that we just specified. And you have here, this will bring you back to this screen where it'll give you the estimates. But let's go over here to the output in Stata to see what it gives us. And also you'll note that here is the syntax. So we just created that model in the SEM builder, and then it spits out the syntax for that. And the syntax in Stata for structural equation modeling is actually fairly straightforward. And so you could get this and copy it and edit that if you'd like. So here we can see the various parts. The intercept on marital quality at wave 1 is constrained at 1. It has a constant of 0. Remember, that's that don't estimate the constants. So the constant is 0 throughout for all the different marital quality at 2, 3, 4, 5, 6, and 7. Now if you remember the slope, we also had an arrow going from the slope to marital quality at 1, but that was constrained at 0. Anytime a path in the model is constrained to 0, Stata won't output that because when a path doesn't exist, it assumes it's 0. The constants will still display, but if a path is constrained to 0, then it won't display it here. We could have just left off that path entirely, but I kind of like to see it there anyway. So marital quality at 2, the intercept's at 1, and our slope is at 1. Marital quality at wave 3, intercept at 1, slope at 2. And then you can see going up. These are just all of the constraints that we already put on there. And now we have the mean of the intercept and slope, and we're really getting to some interesting interpretive things here. So we have here the mean of the intercept is 5.05. And again, that means the mean of marital quality at wave 1 was 5.05. Now the mean of the slope means the average amount that marital quality changes for wives over time, from one time point to the next, from one wave to the next. So from one wave to the next, there is a decrease in marital quality of 0.051. Now the question is that significant? Is there a significant change over time? And this is just the average change, but is there a significant average change? And the answer is yes. This is our p-value, and it's highly significant. So on average, there's a significant decrease in wife's marital equality from wave 1 to wave 7. And here we have the covariance between the intercept and the slope. It's negative and it's significant, meaning that they're related. The higher you start out on your intercept, the lower your slope's going to be. In other words, the more you're going to decline over time, the higher the intercept. And you might have some conceptual hypothesis about why that would be. Now, we're also interested in whether or not the variance of the intercept and slope are significant. So the average is a decline of 0.0518. However, some wives certainly vary from that. Some wives may stay constant in their amount of marital quality over time. Some women might decrease a lot more. Some women might even increase. The question is all that variation significant? Would we conclude that, yes, there's significant variation around that then we might want to predict? And here's the variance of the intercept and the variance of the slope. So this is answering that question of whether or not there's significant variance around that mean of the slope. Now, what you'll notice here is that there's no p-value for that. And I'm not sure why Stata doesn't give those p-values. But here's the 95% confidence interval. And you can't rely on it not including 0 because it's not going to include 0 because of the variance. So what we have to do is we have to calculate that ourselves. We have to calculate the z-value. So what we can do is we can just take our estimate here and divide it by its standard error to get our z-value. So if we display, and this means calculator display, what this is divided by this. So now we just hit enter, and there we have the z-value. And if you remember back to your stats courses, you'll know that higher than 1.96 or lower than negative 1.96 indicates that it is significant at p less than 0.05. So that's far higher than 1.96, and so we are confident that this variance is significant. So there's a significant amount of variance in the slope that we can predict. We could also do this to see if there's significant variance in the intercept, though obviously just eyeballing this we could have told that. But let's go ahead and look at that anyway. Divide the estimate by its standard error, and you get 11. So far higher than 1.96. We conclude that there is significant variance in the intercept and the slope. Now, it's important to note that this is a model of our data that we made up. We said that marital quality waves 1 through 7 should have some kind of relationship to each other, and we said, well, it should have this linear growth relationship. But that was simply our hypothesis. The question is, do the data actually fit that? Does this actually work? And we can examine that using model fit statistics. So we can go here to statistics, structural equation modeling, goodness of fit, overall goodness of fit. Click on that, and there's a lot of different fit statistics here, but we're going to focus just on these goodness of fit statistics right here that's selected by the default. And then here's all the different statistics that could be displayed. We'll just select all of the above, though we'll probably focus on the RMSEA and the CFI. So we'll submit that, and here we have our fit statistics. We have our chi-square fit statistic, which is a measure of absolute model fit. And we don't rely on this very much because it's very sensitive to the sample size. And so we have the value of 98 here, and that's very significant, meaning that our data significantly differ from the model that we proposed. But let's look here at the REMC, the RMSEA. We'd like to see that below 0.6, but below 0.08, I should say. We'd like to see that below 0.06, but below 0.08 is usually acceptable. So we see that our value of 0.072 for the RMSEA is acceptable. That's fine. It's not too concerning. Now, if we look at the CFI, we like to see that this one is above 0.95, and it is. So our CFI indicates a good model fit. Our RMSEA indicates an acceptable model fit. We could probably say that this model does fit the data just fine. It does fit it well. Now, it might be that there's quadratic growth going on here. We're not going to test that in this section. There's another section that will do that in. But based on this, we could conclude that a linear model fits the data well, that Wey's marital quality decreases significantly over time, but then there's also variance in how much it decreases, and we could look for predictors of that to see why some wives might decrease more in their marital quality than others over time.